Hi, I'm Marcello Galhardo. I work in the AndroidX architecture components team at Google. And today we'll be discussing the commonization of the lifecycle libraries to Multiplatform. Before we start, just for set some expectations about the talk, that's going to be a quite technical presentation and is mostly designed for library authors that would like to migrate their libraries from Java or Kotlin to Kotlin Multiplatform. If you're an app developer, you might not apply those things in your day-to-day life, but might still be interesting for you to know how we take these decisions, why we did some of the things we did across the APIs of the lifecycle libraries. For the agenda today, we will be talking about the Android support for Kotlin Multiplatform. And what does that mean for in practice? We will also discuss the timeline to get the lifecycle multiplatform release to stable. And finally, we will talk about the API challenges. The API challenge is going to be the longest part of the talk, and it's going to be mostly code. The code is simplified, and it's just the idea to show what were the challenges and how we solved them and why we did what we did. So back in 2017, we did announce the Android architecture libraries, which included ViewModel and Lifecycle. At the time, we did have a Java-first ecosystem, and people were still using the traditional UI toolkit, which was based on Vue and XMLs. That was a completely different world from today. And this year, in 2024, we did announce that we officially support Kotlin Multiplatform on the Android platform. And now we do have Kotlin was the first language in Android. We also have the modern UI toolkit for Android Compose. And this is very different from the world that these libraries were designed for. So what does that mean, KMP support, supporting the Android platform? Essentially, there are two levels of support. One is the KMP compatibility, and the other one is KMP support. For KMP compatibility, the idea is basically that we make your code available, we make the library code available on common source sets. So if you're writing your Kotlin Multiplatform project, you can just use this code in your common main, and that is workable. However, you might need to integrate it by yourself. So if you're using Lifecycle, for example, Lifecycle is a library that has KMP compatibility. If you do use a library that integrates with the Lifecycle Multiplatform, which one of them is Navigation Compose provided by JetBrains for Kotlin Compose Multiplatform, this gets for you out of the box, but if you are integrated by yourself, you might need to write your own local lifecycle owner and call the methods in the right point to make everything work. KMP support is similar to compatibility, but everything works out of the box. You can just integrate that in your library, in your project, and things will just work. You don't need to do any manual integration if you're not using a specific library. An example of that would be Room. With Room, you can just include that in your project, and things just work. So the timeline to get the Lifecycle KMP stable release. The project spanned from January to May in 2004. Our goal was to actually get Navigation Compose Multiplatform released. And what happened mostly is that we did collaborate with JetBrains. They are very excited to get a navigation solution to Compose Multiplatform, and we are excited to enable them to do that. So while they were focused on the navigation KMP work, Compose KMP work, we were focused on how to make it easier for them to get to that point. So we were up ahead in time trying to remove the dependency and make them multi-platform before they get to a first release. We did sync with them regularly, and we did collaborate a lot during this project. From our side, what we did was we tried to understand what was the main dependence from the navigation Compose Multiplatform, and we did try to get them to KMP first. So Lifecycle Common, Runtime, ViewModel, ViewModel Compose, and so on. And we did really want to get a stable release because we want basically to have a guarantee that those APIs that are KMP compatible would not change later on. So we want them to build on something that was stable, that they don't need to worry about APIs changing and so on. So before they get the first alpha, we did get all the lifecycle libraries to stable. So for the API challenges, that's going to be most of the talk now, and we're going to see a bunch of code. And let's start with the lifecycle event per platform. Again, if you're using Navigation Composer Multiplatform, that comes for you for free. If you're not, you might need to call the methods in the right point. If you're doing Android development for a while, you might be familiar with the famous Android Lifecycles methods. So you do have things like onResume, onPause, and so on. But it seems that it actually translates quite well for other platforms. For iOS, you do have things like did become active or will resign active that can be mapped respectively for onResume and onPause. For desktop, it's also similar. You have window gain focus, window lost focus, and so on. The web is much simpler. For web, you do get focus and blur, and we just skip most of the lifecycle. We just move to that point and move out from that point. There is no way to map the others quite well. JetBrains has a public documentation on that they explain very well how each one of them work and how they did everything if you're more interested. Okay, for the view model class, view model provider class. So if you just learned Android, you probably didn't have to use the view model provider directly, but you have been doing Android for quite a while with Java, etc. You probably interacted with the view model provider. So the view model provider is essentially the main API for view model. If you're using active, that's done by calling by view models the extension function, the proper delegate, and behind the scenes, you're actually using the view model provider. With compose is the same idea, but it's the view model composable function. And these two functions, in the end, at some point, they're going to create a view model provider, passing a view model store factory and extra, passing a key that represents that view model, which is normally a string, and the view model class that's going to be instantiated. So let's look at the view model provider class. This is, again, a simplification short version of the class, just the methods that we're going to be covering. We do have a constructor, which is annotated with JVM overloads, and take the view model store factory and extras. What normally happens is, in case of a configuration change, the view model store is going to be retained in memory, and it's going to be passed to the system for retention. And once the view model provider is recreated, you're going to receive the same view model store, and you'll be able to retrieve that. If there is no view model in the store itself, then the factory is going to be called, and it's going to create a new instance and put in the store. And the creation extra is just an add-on that allows you to configure view models. The get function is the one that actually orchestrates all of that. So you just pass the key and the model class, and it's going to be responsible for seeing if the view model exists in the view model store. If not, creating with factory and put it in the store. The factory interface is essentially a factory that creates a view model. So it takes in the class that you want to create, and also some creation extras that allow you to configure that instance. There are two default implementations for the factory. The one is the new instance factor. This is essentially when you create a view model without passing your own custom factor. This is going to create the view model using the no-args constructor. The other one is the Android view model factor, which is a specialization of the new instance factor. It does essentially the same, plus it also supports if you have an android.app.application. And the companion object just adds some utilities and extension functions that you can use and properties with the view model provider. So let's get back to the constructor. If you do take a look in this method signature, you're going to see that we do use something called JVM overloads, and we have an optional parameter in the end, which is empty. It's essentially an empty map. The thing with the JVM overloads here, that JVM overloads will take care of Java interoperability, and essentially supposedly we're going to create two methods. One is going to be that does not has the extra parameter, and by default use the empty. The other one is going to require the extra parameters. So Java clients can call this method with or without the extra parameters. So far, so good. So if we do theoretically move this method to from Android main to common main, for example, to make it available for common, it should work because this should only work on JVM and seems reasonable. So we could try to take the viewModel provider constructor and move it from the Android main to common main, and we would expect everything to work. To be sure that everything works and we didn't change anything, we can actually run in the AndroidX repo. Essentially, in the AndroidX repo, we do have some tooling to verify API changes. So whenever you do any type of change, you always are going to run against this tooling, and you're going to be sure that nothing changed in the binary level in Java bytecode. And in this case here, we can move the file, and we can run this tooling to be sure that everything works. So that's done by calling Gradle check API. If you do clone the AndroidX repo, you can call this method, and you're going to get the output from that. So for us, the output is by moving that from Android main to common main, a constructor has been removed and another constructor has been added. The two of them have the same number of parameters. They store the factory, the default creation extra. However, like something changed. So if we look closer, we're going to notice that before there was an optional keyword on the last parameter, and this disappeared now. So again, we need to investigate why that happened, like what caused the binary change. One idea that we can do is, on Android Studio, for example, you can go to Tools, Kotlin, decompile Kotlin bytecode, if I remember correct, and then you can decompile the code before and after, and do a diff between the two of them to understand what has changed between the binary code of the two. So by doing that, more or less what we're going to get is this output. The first two methods is what you would expect from the JVM overloads. You have one that does not have the creation extra. You have one that has it, and guarantee interoperability with Java. However, Kotlin also introduced the third method when you do that in Android main, which is a syntactic method, which is public, takes in the default constructor marker, and it seems that is used for optimizations that the compiler does by itself, which means someone compiled against the lifecycle library might be using this method even though they are not intentionally using that. The compiler can make them use that for optimization purposes, which means this is a breaking change and we cannot just remove this method. Otherwise, someone using an old version that ends up running against a new version would not be able to call this method and it would not compile. So essentially, JVM overloads in common code and expected declarations does not generate the syntactic default constructor, which is a binary incompatibility change. There is an issue open for that. So we will need to handle that by ourselves. One way to handle that by ourselves is essentially do more or less what the compiler would do for us, but we're going to write that ourselves. So we cannot touch the JVM overload method, but we can introduce a new create method that takes exactly the same parameters and just call the viewModel provider constructor. And this essentially for Kotlin multi-platform clients, you can still call the create method, but any Android or anyone that used the lifecycle library before can still access the old constructor. So essentially the learning from this one is just by moving files, you can actually change the public API if you don't have a tooling to assert against that. So ideally, if you are maintaining a library, you should have a way to validate that. For us, we do have integration. Like we have a library that I think is ours, called MetaLava that we use for validating our API. There is also one provided by JetBrains that is the Kotlin binary compatibility validator that you can integrate in your projects. The MetaLava is, as far as I know, is open source, so you can actually check the code online. So next, the get method is the one that does all the orchestration, takes in the key string, a model class, and it's quite straightforward, returns a type that extends the viewModel. If you expand the model class, we're going to see that there is a java.lang.class, and as the name suggests, java.lang is not available on all multi-platform libraries, just in Java. So we need to do something about that again. Here is quite easy. We just need to introduce a new method that takes a key class. But again, for binary compatibility, we also need to keep the java.lang.class. So we just call one from the other, and That's basically it. If you're using common code, you can just use the key class variant of that. If you're on a Java client, the java.lang.class still works as expected. And by doing this change, we actually some people report some issues. Essentially, people that use mock libraries where, I don't know why, but mocking the view model provider get function. And now that there are two methods that have the same number of parameters and the type is not specified, the mock libraries are not able to distinguish between the two of them. They are binary compatible. They have the same behavior, but the mock library is not able to understand which one of them is being actually asserted, verified, and so on. So that essentially breaks some tests that mock that. So the learning here is essentially, I think, two. One is that you definitely should not mock the view model provider, but overall, do not use mocks. That's easier. Yeah. Next, the factory interface. It's essentially, again, a simple interface, has one method. Actually, has more than one method, but for here, it's going to be just one. Takes the class, the creation extra, returns the view model. Again, this has the same problem. It takes in a Java Lang class, so we're going to do something similar now. We're going to do the key class, call the other one from the new one, and things would still work as expected. And actually, the default implementation is unsupported operating exception. So it just throws if you don't implement. And the learning here is for us. If you do have Java types that are in your public API, you will need to handle that somehow. They are kind of a hint of things that might be problematic when you're migrating your library. So keep in mind that any public API with Java types might not have a common available API on KMP. Right, for the new instance factory, the default implementation of the factory interface, if we expand the content, we're going to see that it calls model class .getDeclaredConstructor.new instance. And essentially what this does is it uses reflection, gets the declared constructor, which is going to be with 0 arguments, and going to call new instance, instantiate that view model. So Kotlin Multiplatform has something that offers that, which is the create instance from the key class, but that's inside the kotlin.reflect.full. That is not necessarily a small package. And we did not want to have everyone that use lifecycle libraries, which is a lot of people, to get these in their apps by default. So essentially here, our learning has been, it's not worth it to actually implement everything that our libraries has in all platforms. Sometimes it's fair to just, in some platforms, that functionality does not make sense, and it's okay to not bring them to all platforms. The Android view model factory, it's essentially the same as the previous one, but covers the android.app.application. The Android app.application is an Android-specific class. Wouldn't make much sense to have this on the common code anyway. So this is also not commonized by us. Not everything has to be commonized. So if you're bringing your library to multi-platform, you don't necessarily need to commonize literally all the methods and everything it has. If something does not make sense, it's fine to not bring it. Okay, so now that we decide what we actually want to migrate to multi-platform, let's migrate the view model provider. On Kotlin Multiplatform, if you're familiar with it, we do have the expect and the actual keywords that you can put in the beginning of a class. And essentially what this does is you define something that is expected, but without the implementation. And then you can have an actual implementation of that class in multiple platforms. Each platform can implement that in different ways. As long as they comply with the defined public interface that is expected. For us, we don't want to bring everything, but we do want to bring the get method, the factory interface, and the companion object. And our first intuition here would be, okay, the get function is kind of simple, and probably we do not want to have a different implementation of get per platform. Probably we can just put a default implementation and just care about the things that change, because we cannot just make this a common class because of the method that we decide to not bring in, like the constructor, new instance factor, and the Android view model factor. So abstract class has default implementations. Interface in Kotlin also has default implementation. You would expect that to work. But expect declarations do not support default implementations. So we actually need to do that by ourselves, essentially writing the code that the Kotlin kind of should generate for us. So if we do count the number of view model providers when we did these changes, we would get 3 of them. We would get a view model provider for desktop, for Android, and for non-JVM. That includes everything that's not JVM. So this is 3 implementations. And we do not want to actually have those 3 implementations. We don't want to triplicate this code for the get function or for any code at all. So if we go back to the actual implementation of the view model provider now, what we can do is we can leave the constructor, which, as we said, is going to be for JVM applications. And we can just care about the get function, and we can extract that to another class, which essentially is going to be the one holding all the behavior and data from the view model provider. And we will basically be implemented by ourselves what would look like a default implementation in the Java bytecode. Essentially, we get a view model provider implementation. This view model provider implementation, which is the new class that's going to be shared, is created in all the constructor, and all the methods simply call the next method on the view model implementation, which has the actual behavior and code that's shared. Any specific code will still be held in the view model provider that's actual, but any shared code is going to be shared with the view model provider implementation. That's quite simple. So we just extract the news class. We call the method getViewModel when the getViewModel is called, and things should work. And if you didn't notice before, we cannot use a java.lang.class. So it seems reasonable that we change the getViewModel that's shared across all platforms to a key class. And by doing that, we can just call factory.create model class, model extra. Things should work. The rest of the implementation is exactly the same. We don't need to care about that. And everything compiles and theoretically works. And by doing that, we actually reverted a 2-year-old fix because there were some special cases around the view model factory. Essentially, when you had a desugaring for compiler-only dependence in a library project, that method would be desugared, would not exist, and trying to access that would throw abstract method error. Essentially, this means that we kind of broke leak canary users, for example, and we had to backport the fix and fix that. So let's see how to fix that. We take the factory.create that takes the key class and the model extra, and we're going to introduce a new function that's going to be the createViewModel. Just a common top-level function that takes the 3 parameters. The createViewModel, as well, is an expect function. For all platforms that are not Android, you can just call the method. Everything works as expected. For Android, however, we do need to call the factory.create passing the key class and creation extra. If we do get abstract method error, we try calling the Java variant of that. If we do get abstract method error, we try to call the Java variant without the creation extra, and this kind of fix it. We did write tests and put things in place to be sure that we don't revert that by mistake. But yeah. So essentially what we did here is we have a view model provider that is an actual implementation per platform, desktop, Android, and non-JVM. Those call the view model provider implementation, which is a shared code among all platforms, which again calls a createViewModel, which is a specific implementation for each platform, desktop, Android, and non-JVM. So you essentially can mix and match the actual expect to share or handle as much as you want specific per platform. So the learning here is essentially many. One of them, there is no expect class in the full implementation. So if you want to share code, you're going to need to do that by yourself, however you choose. The sugar minification can cause side effects, and they're quite tricky to actually find and spot. So I don't think I have a good solution for that, but essentially once you catch them, try to put mechanisms in place that you can detect them again in case something causes it to come back. And finally, you can mix and match expect and actual, with common code for reusability. And this is kind of powerful because you can share code as much as possible while leaving small pieces that are expected per platform, and you can change the behavior of the platform, and you can do that as many times as you need within mix the two of them. The only thing that you need to be aware when you do something like that is you do now have more branches of possible behavior that your code will go through. So you want to have tests that for sure guarantee that all of these paths, Android, non-JVM, desktop, would behave in the same way or very similar, would not crash your clients. So you might need to actually make more tests in some cases. Okay, so the view model class. The view model class, I think anyone that uses view model library probably knows what is that. The two APIs that we want to cover here is essentially the add closable, which is a specific API that allows you to bind a resource to the view model. So if you do have something that needs to be cleared together with the view model, you can use the add closable to add a closable, which is going to, whenever there is uncleared method called, you're going to call the close of the closable, and you're going to have a chance to clean these resources. If you do pass a key string, this key allows you to identify the closable, and you essentially can retrieve it passing the key again if you need to interact with these resources multiple times. We do use that ourselves, so we're actually going to show a use case of this. And there is the view model scope, which is our coroutine scope support, which you're probably familiar with. Essentially allows you to get a coroutine scope that is automatically binding to the lifetime of the view model. For the closable API, if we do extend the types, you're going to notice that this is a java.io.closable. As before, Java types not necessarily all available on all platforms. However, java.io.closable does extend java.io.outClosable. And this is actually backported to Kotlin Multiplatform. So essentially, there is a type alias for outClosable that if you can use that in all platforms. On JVM platforms, you're going to just use the actual autoclosable. For other platforms, they implement it by themselves. So we can change that from closable to outclosable. We can change the signature, use the Kotlin outclosable type alias, and essentially that would work because they implement each other, so it's fine. However, we did get lucky here because the two add closable that takes in the key were not stable at the time, so we don't need to care about backward compatibility because we don't expect people to actually expect guarantees of binary compatibility on APIs that are alpha. So the problem here, though, is the first method was actually a stable method. So if we would simply remove this method, the first one that does not take the key string, and there is someone that has a library that is compiled against the old version of the view model, and by some reason it ends up at runtime with a new version, that method would not be available and exist, and this would cause an error. We can handle that in Kotlin by using the deprecated annotation. The last parameter, deprecation level hidden, means that only whoever is already compiled with the old version can actually access that. And any new clients, we are not able to even see this method. And we need to leave it with the java.io.closable as before. So we can count the number of implementation of the view model again, like we did before. And this time we only have two, the JVM and the non-JVM. So we're going to need to do something similar that we did before. We're going to introduce a view model implementation, which holds the view model behavior. It calls in the add closable API and get closable API from the implementation, and the view model actual implementation does anything, essentially, or close to anything. So the view model implementation, it's essentially the same code that was in the view model. However, there is one thing that I want to call attention here, which is there is a lock mechanism, a synchronized object. The reason we have that here is because whenever you add a resource and this resource is cleared, we do not want to leak this resource by mistake or create multiple resources if it's in a multi-thread environment and so on. So we want to be sure that all the closables that are associated with the lifetime of a model would always be unique and would be cleared correctly. And, there is lock support, synchronization support for Kotlin Multiplatform, and that's provided by JetBrains in a library called Atomic Foo. That's the README of the Atomic Foo library. If we do look closely in this README file, there is this small warning that says that the Atomic Foo locks package is experimental explicitly, even when Atomic Foo is experimental itself, and there is no guarantees whatsoever. So we cannot just put that in our libraries, and they might change and break compatibility at any point. We will need to implement that by ourselves based on the platform that we are. We can do that by introducing the expect class for synchronized object, inline function for synchronized that's final, and a synchronized implementation, which is also expected. You might notice that there is weirdly one synchronized function and one synchronized implementation function, which wouldn't make that much sense. The reason we need to do that is we do want to pass more information for the Kotlin compiler. We want to use contracts for that, and contracts are not supporting expect functions. So we need to work around that by introducing a non-expect function and calling the expect function from the non-expect function and define the contract in the final one. Again, there is an issue open, and hopefully once that's fixed, we don't need to do this type of thing again. So for GVM, it's quite easy to implement that. We can just call the Kotlin.synchronize method. The API signature is essentially the same. We're trying to keep consistency here with their signature and contract, and everything we're going to work. For native, however, we do need to implement that ourselves. We do that by calling the lock method from the synchronized object and unlock when the action is finished. The hard part here would essentially be the actual class synchronized object. If we do expand the content of synchronized object, there would be a lot of things here, but what I want to call attention is the experimental foreign API. Something really, one of the main advantages of Kotlin Multiplatform is that you can access native resources when you are essentially, if you are in a specific platform, you can actually access the native APIs from this platform. This gives a lot of power and flexibility because you don't need to use a bridge to connect with underlying system. The side effect of that is that, like, as an Android developer, you also might need to access those APIs, and you might not be familiar with how they work or any of that. So, and even those APIs, some of them is going to be experimental for Kotlin. So you will need to get used with essentially touch those native APIs, and from time to time, like eventually, while the ecosystem gets more mature, people will provide libraries that actually handle these things for you. You don't need to worry about that, and so on. But from time to time, you will need to touch those APIs. We need to get used and comfortable with them, and and also test them. Another weird thing here is that there is a expect val mutex recursive flag, which is an integer. So why would you actually have an expected for an integer? So essentially, numeric types with different essentially there are recursive flags that represent numeric types, and this representation is different depending on the platform. So if you're in a platform like Linux, you get a unsigned integer. If you're in a platform like Darwin, you get a signed integer or normal integer. So you need to also handle this small difference, which is just verbose. So for us, that is essentially defining a expected property. We have, for the Darwin, we just use the integer. For the Linux, we just convert the unsigned to signed, and that's it. Right, the view model scope. For the view model scope, We do use the methods we just implemented, actually. We do use the synchronize. We use the get closable and the add closable. And we also have something called closable coroutine scope. The closable coroutine scope, it's a coroutine scope that implements out closable. It's connected to the view model using the previous API we just showed, add closable, and that binds it with the view model. The point that is interesting here is the dispatch.main. This is not available on all platforms, and they might behave slightly different on each one of them. So we will also need to handle that ourselves. We can introduce a create view model scope function that we're going to use that different from the previous examples. We are actually not use expect and actual function for handling this. We're going to handle this for all platforms in the common code. So the create view model scope will look essentially like this. We're going to introduce a normal function. This normal function, we have a huge try catch block. And if the dispatcher main is available, we can just return that and go on with our lives. If there is a not implemented error, this happens in native environments such as Linux. And for this case, we're going to fall back for the empty coroutine context, which is the default one. For JVM desktop environments, such as desktop with swing, you're going to throw a legal state exception. We again fall back for the empty coroutine context. And finally, we're going to call the closable coroutine scope, passing the dispatcher plus the supervisor job. And yeah, essentially, although expect and actual is quite powerful, there are some cases that might be just easier or make more sense to not use them and handle the case by yourself in the common code. So don't feel like you do have to use expect and actual for everything. So we did essentially cover some of the API challenges for the lifecycle libraries that we transform, or at least the ones more interesting and weird. So let's take a look in the takeaways that we got from this experience. The first one is that it might be a bit challenging to find what's the minimal change we can do against the best possible common API. We do want to give Kotlin Multiplatform clients the best API possible that they can have. At the same time, we do not want to break apps that already exist built on the old APIs or Android. We want to be sure that those APIs are solid and there will be no side effect by building better common APIs. And striving for this balance can be quite difficult, and this is a learning process as well. The other one is if you do have a library that has a lot of users, you can reuse the knowledge that you already have. You already have APIs in place, even if in case like ours that we had to duplicate some of the methods, try to keep consistency, try to use same names, try to see from your users how they use those APIs and what makes sense to bring to each platform or not. You don't need to reinvent everything and rebuild your whole library just for a KMP, for example. Finally, Kotlin Multiplatform is quite powerful. We did have a bunch of roadblocks and faced some issues, but at the same time, that was a library that has been built 7 years ago for Java, and we are converting it all the way to Kotlin Multiplatform, which includes all the different handling of types, platforms, and so on, and we did manage to get that. That just shows how powerful Kotlin Multiplatform is today and how flexible you can use what is today available. Yeah, that's all I have for today. Thank you.